Let us review the 3D side of the 3D aspects of components for forces. So we by now should know how to do the 2D, which we've talked about it many times. So it's the cosine and the sine of the components. And 3D is is just the same thing. Just make sure you don't get confused about which angle you use. So if they give us a system of forces, or just one force, and they give us the coordinate system. So in the case of a coordinate system assigned, we just have to use that coordinate system. So they're telling us that there's a force starting from origin, which is very nice. It would be a little difficult. It will be just an extra step to compute the direction or the coordinates of this force if it's not starting from the origin. If it's not starting from the origin, you have to do the end the end coordinate minus or the end coordinate minus the starting point, right? So we'll have an example about that later. But in this case, starting from the origin, so this point is origin has coordinates 0, 0, 0 in I, j, and k. So it's pretty simple because whatever coordinates you have at A, it will be minus 0, then just the coordinates of, at A. The coordinates A will be x at A, comma, y at A, comma, z at A. Okay? The coordinates are right there. All right, those coordinates they're telling us that they have an angle phi with respect to x and theta y with respect to y. Okay, so the force is given and the projection is like so. So the force, as you can tell right here, has components Fy, Fx, and Fz. You have three components, x, y, and z. So what they're doing here is first they're projecting the force to the plane, to this plane, which is a pretty good step. This is the easiest thing you can do right now. So when you project it, you will have the angle, as we mentioned before. You will have the angle phi and say the angle alpha. Okay, and we know that alpha plus, this is phi, phi equals 90 degrees. Okay, so if they're asking us to find Fy, it's pretty simple. Fy is equal to the force, and this is the cosine, okay, times cosine of theta y. That is Fy. If we want to find Fh, which is this guy right here, this component that we can move to the plane, we can do two things. Either we say that we have this extra angle, let's say beta, and we know that theta y plus beta is 90 degrees. So we can do either, they call it FH. So FH is equal to F times sine of theta y, or FH is equal to F times cosine of beta. These two things are the same because the angle will tell me if it's sine or cosine. Okay, so if I do sine, I'm getting this component, which is FH. If I do cosine, I'll have to use this angle, the angle right here. Okay, let me fix this angle a little bit. this is phi. Okay. All right, so fh is that. Now, if they're telling us, please compute fx and fz, well, it's pretty simple. We only have to do fx equals fh times cosine of phi. But fh is all this thing right here. So we can say that this is equal to f times sine of theta y times cosine of phi. Okay, and then if we want to compute fz, it's just the sine of it, of the angle phi. Fy equals fh times sine of phi. Okay, this is equal to f times, if h is this thing right here, f times sine of theta y times sine of phi. Okay, so the components of this force are, in terms of cosines, this is right here the representation of the cosine of the vectors, cosine of with respect to theta x, with respect to theta y, with respect to theta z. So why are we getting that? Because notice that here they gave us theta y, so we could do this. In fact, we got that. It's f cosine of y. But they didn't give us this angle right here, which is theta z, and they didn't give us this angle right here, which is theta x. They tell us what's the angle of the projection. So this is the representation of the force with respect to the angles, with the theta angles. And this is the compact form. In our case, which they give us a different set of angles, which is the projection of force is equal to the actual vector times, in x we have cosine of theta. Actually, it's not cosine, it's sine of theta y times cosine of phi in I, comma, cosine of theta y in j, comma, sine of theta y times sine of phi in k. So this is how we represent that vector. Okay, so it's pretty easy. It's just a longer expression. And again, let me fix this. Okay, so if you go to your book, you should actually have that same example right here. I took it from the book. And yeah, so just basically telling you is if it's sine of theta y, cosine of the angle, sine of theta y, and sine of phi, and the force is just the square root of each component. Let us look at this example right here. We have this vector, this force from a point M, it's not origin, going to a point N, away from origin, and we want to find the coordinates of, or the distance better, the distance of the point M from the point N. So remember, you start from the head, and you go to the tail. So the distance is We're gonna have components in x, y, and z. X is going to be x2, the head, minus x1, the tail. x2 minus x1, y2 minus y1, z2 minus z1. That is the distance in vector form. The magnitude of the distance is square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. Just like that. It's not x2 squared minus x1 squared. No, is this actually, if you have the numbers, maybe you just want to compute that first and then bring it to find the magnitude. Let us look at this example. There's a tower that is using a wire with a tension of 2500 newtons. So either we draw the force like this or like that. We have to choose. So I would say let's draw it like this. Both ways we should get same answer, except for maybe we get a negative value for the answer, but it's just telling us if it's compressing the cable. So let's draw it like that. All right, determine f, x, y, and z, the forces of this vector. Okay, so we're gonna have it here. They're asking us for the coordinate system, so we can put it, the dimensions are based on this point. So they're basically telling us that this is the origin, this is I, let's do it, this is J, and this is K. I, J, and K. Okay, we have the coordinate axis. Basically, it's going to be like this: X, Y, and Z. That is our origin. So the distance of X is going to be the head minus the tail. So that's another reason why it's easier to do this way. The head is going to be 0. So distance in x is right here is equal to 0 minus 40 meters. This is equal to 40 meters. Distance in y is equal to, y is up, 80 minus 0, 80 meters. The distance in z is going to be, remember z is positive, this direction. So it's going to be 0 minus 30. Minus 30, which is equal to 30 meters. So 40 is negative 40, 80, positive 80, and positive 30. Okay, we're good. So the vector A, B, and the vector is written tail to head. A, B has components negative 40i, comma, 80j, comma, 30k, and all that in meters. If we do square root of that, it's 94, and the unit vector is AB vector divided by AB magnitude. AB magnitude is this guy. So that means that we have negative 40 divided by 94, comma, 80 j 80j divided by 94, comma, 30k divided by 94. Meters divided by meters, this is unitless, and we get, let us see, the calculator. Forty divided by 94 equals 0.42. I, comma, 80 divided by 94 equals 0.85 j, comma, 30 divided by 94 equals 0.31 k. But remember, this is negative. Okay, so our lambda, which is the unit vector, is negative 0.42 in I, positive 0.85 j, and 0.31 k. Okay, so the tension, you can call it T, is equal to the force times lambda, which is equal to 2500 newtons times this vector. And that gives us 2500 times 0.42, and this is negative 1050 I, comma, 2500 times 0.85 equals 2125 j, comma, 2500 times 0.31 equals 775. Okay, so I wanted to show you that even though they're not exactly the same numbers what the book gets in our calculations, this is fine with me because we're rounding up. They got negative 1060, I got a negative 1050. This is okay. In the z direction, they got 795, I got 775. This is okay.